Now, let's solve the problem for thermistor. A thermistor is used to monitor room temperature. It has a resistance of 3.5 kilo ohm at 20 degrees Celsius with a slope of negative 10% per degree C. And the power dissipation constant is given at 6 milliwatt per degree C. This thermistor is used in a divider that able to provide a voltage of 5 volt at 20 degrees Celsius. Now, the question is, evaluate the effect of self-heating. So in this question, we are required to evaluate the effect of self-heating, meaning we need to consider the self-heating temperature into our calculation. Without considering self-heating, it's already given that at 20 degrees Celsius, the voltage output will be 5 volt. This is due to the resistance at 20 degrees Celsius is 3.5 kilo ohm. So therefore, V out is equal to 3.5, the resistance for the sensor divided by the total resistance, which is 3.5 kilo ohm plus 3.5 kilo ohm, which equal to, multiply with 10 volt, the power supply, that will give us 5 volt. So that is correct for the theoretical value of 20 degrees Celsius. It will provide 5 volt. But that calculation doesn't consider the self-heating effect that is occur in the RTD. So first, let's calculate the power losses and then calculate the self-heating temperature. So in order to calculate power losses, we need to calculate the current. So the current is equal to V over R, which is 10 volt divided by the total resistance, which is 7 kilo ohm. This will give you 0.01 ampere. From there, power is equal to 0.01 square multiplied with 3.5 kilo ohm, which give you 0.071 watt, meaning there is power losses about 0.07 watt due to the current and resistance in the RTD. So from there, we can calculate the self-heating temperature, which is 0.071 divided by the power dissipation constant, 0.06, give us 1.19 degrees Celsius. So this self-heating temperature tells us that the thermistor is not measuring 20 degrees Celsius, but is actually measuring at 21.19 degrees Celsius. So instead of using 3.5 kilo ohm for 20 degrees Celsius, now we need to get what is the resistance value at 21.19 degrees Celsius. So in order to calculate that, we consider the slope information given in the question. So the slope information says that at 20 degrees Celsius, the value is 3.5 kilo ohm. Then it has a slope of negative 10% per degree C. So meaning that the resistance value will decrease by 10% if the temperature increase by 1%. 1%, it will increase by, for 10%, it is 350 ohm. So now, the RTD have self-heat itself by 1.19. So the temperature has increased 1.19 from 20 degrees Celsius, which give us, it will decrease by 416.5 ohm. Therefore, the resistance at 21.19 degrees Celsius is, we have to minus from 350 minus 416.5 give us 3083 ohm. So this is the resistance at temperature 21.19 degrees Celsius. So let's see what happened to voltage output since the resistance value has decreased. Using the voltage divider equation, we can calculate the voltage output is equal to 3083.5 divided by 3,500 plus 3,083.5 multiplied by 10, which give us the voltage output is actually 4.68 volt. Okay, theoretically, we consider at 20 degrees Celsius, without considering self-heating, it will give us 5 volt. But when we consider the self-heating, the real phenomena that occurred in RTD, due to the power loss, the RTD have self-heat itself by 1.19 degrees Celsius, meaning it measuring the resistance, the temperature of 21.19 degrees Celsius. Then the resistance that represent 21.19 is 3083 ohm. From there, we calculate the voltage output is actually 4.68 voltage, not 5 volt. So that is the effect of self-heating.